to have a Jun again. He was not giving a talk at this Extremal seminar for a long time, right? So this is your second talk, maybe?
Yeah, it's okay.
Yeah, please.
Thank you for coming. Today I will talk about the degenerate gram problems in p-normals. And this is a joint work with Xizhi Liu, Jun Gao, and Oleg Tikov. And that's before start my talk, I will give some definition of the degenerate gram problem in p-normals. And today we will consider the hypergraph. So given R graph. R graph means R uniform hypergraph. Each edge contains exactly I vertices. And given a family of I graphs. F. We say graph G is F-free. Means the graph G does not contain any member of the family as a subgraph. And the p-normal means the sum of the piece power of the degree, or piece power of the vertex degree, then it will equal to this number.
So you don't take the power of 1 over p or
No.
something? No.
If you take it, also have some other name. Then for the case p equals to 1, it will be I times the number of the edges. Our problem is so we want to know if we forbidden some family of the graphs, what is the maximum number of the p-normal of the graph. So the power of it doesn't matter for this problem. We are not the first group for studying these problems. Then let's give some history of the problem. In 2000, Cairo and Houston considered these problems for click, has and C4. And in
for graphs, right? For 2 graphs, right?
For two,
You stated the problem for hypergraphs, but this is for
yeah, this is for 2 graphs.
okay.
All the research before it's for 2 graphs. This is for 2 graphs. Proved in 2009. He proved it. even cycle, if p is at least 2, then this will equal to this number into p. So p is at least 2.
So here they know, you actually know the answer for P is up to this little arbitrary
Yes, means this is exactly.
Mm.
And for the lower bound, the construction is like this. K minus 1 vertex minus k plus 1 vertex, and all the edge between 2 parts and in this part. You can't find the cycle of length 2k.
If you forbid KK, does it change? I mean, we know for KK, we know the answer for P equals 1, right? Does it change
For complete bipartite graph.
for complete graph
For complete graph.
on K
The
vertex?
KK it will be
It's just the same.
Yeah,
as,
right,
It's
right.
always
But,
always the same, no matter what P is.
yeah, and always,
Yeah.
but the relation may be different, not balanced.
I see.
Extreme graph may be not balanced,
I see. So it's always K
but always like this. Because a result of average states that every KK free graph, you can find a K-parted graph such that each vertex have larger vertex degree. Yeah, so this
I see.
structure will always give the extreme graph.
Do you assume the p is integer or?
Yeah, before they always assume it, but here we only assume p is at least 1. Because for the degenerate problem, all the construction for the lower bound is some pseudorandom graph. They are almost regular. So when p is no more than 1, it will equal to the Turán problem. So we only consider p is at least 1.
And for the Kiporof's result, when p is like, for instance, 1.99, then it's
If they didn't consider,
didn't consider.
they didn't consider it.
You're not saying it false, right?
Yes. And there's also some other result for some special graph. I will not introduced here. And let's see. So here we will only consider the degenerate gram problems. So let's see what is the degenerate. If the Turán density is 0, we call it is degenerate. Turán density is this. And we know this is if and only if f is r graph. And a family is degenerate means it contains some degenerate graph. So we want to know the relation between the p-normal to a number and the to a number. Let's say some lower bound of the problems. Here we assume p is at least 1. And when lower bound is come from the Turán graph. By the convexity we have the p-normal is at least n times into the every vertex has the average degree. This will be the minimum. So this one will larger than this function. This is by and another construction is similar as this, some star-like structure. Before this, we see a new definition. We call it independent number, independent covering number. This number is the minimum size of a set, such that every edge intersects this set only one vertex. And for family will be the minimum value. So similarly, this construction will give us the lower bound. This part is n minus this part, and we take all the edge with exactly one vertex from this part. Then this graph will not contain any member of this family, because the induced covering number means a set intersects each edge exactly one vertex. If you can embed it into this part, this set will be the induced number will be smaller than our definition. So this will be another extremal graph. And this graph
So this number, for some hypergraph, this tau of, this independent covering number is not defined, right? Because maybe you don't.
Yeah, maybe not. Yeah. But for the bipartite graph, each part is independent covering. Each part satisfies this condition.
I see.
Yeah. So we have a lower bound. Is like this. For coming just little one. We have this lower bound. So we want to know when the extreme graph is look like this, when the extreme graph is looks like the Turán graph. And before state our main result, we will give another definition similar to this one. We call it partition number. The partition number is we know this graph is bipartite, but maybe it have many different way to partition this graph. The partition number will be the minimum size of some part in all the partition. Minimum S argument S R partition. So clearly we have, because this S will also independent covering. So we have this number is no more than partition number of the F. But similarly, we can define the family of the partition number. Okay, let's state our main result. We prove that if the Turán exponent is no more than 1 plus alpha, here we need alpha is between I minus 2 to I minus 1. If the alpha is no more than I minus 2, it's still open. We don't have don't have way to solve it. Then the p number will equal to this is come from the fast construction. If p is no more than I minus 1 minus alpha, and for p is large, it is no more than this number. If p is at least I 1 over I minus 1 minus alpha. And for the case equal, this will, for p equal to this number, we have 1 plus p times alpha equal to n to the p. So this will be, these two extreme graphs will give the same upper bound, but we cannot prove it for the best possible. We have log factor here.
Can I ask some silly questions? Because I
Okay.
trying to catch up with the definitions.
Yeah, I will mention more about
So
this.
gamma partition is partition into gamma sets, or so when you say F has gamma partition,
Oh, sorry, R partition.
R partition.
R.
So that means you wanna have a partition into
So
R
we
many.
have a partition into many, such that each edge use exactly one vertex in each part. This is a
Oh.
partition
I see, because it's R that.
because it is a R graph, R partite graph. So maybe we have different way to partition it. Then we take a minima as.
So in the bound, you're referring to the R part and not R independent.
Yeah, this is for R part. The lower bound is for R independent.
I see.
The upper bound
I see.
is
This
for
so this is
partition
just the
number.
upper bound. I see.
Yeah, this is just
All three of the upper bounds.
upper bound.
Yeah, yeah. Okay.
Oh, here is maybe no more than enter.
Gotcha.
Yeah. And actually, the case for R equals to 2, have some people analyze this result. Remark, but but nobody noticed their paper after we submit our paper to archive. Further and print again, improve, wait. They proved this, and they don't have this constant vector. They proved a bigger O of this for the same result for the case I equals to 2. But all of the history didn't find this paper. So after we submit it, somebody tell us we have a result about this problem. Yeah. And we them also conjecture that this log n can be removed. Yeah. So
somehow though, given a graph, you don't really know what alpha is.
yeah, actually, if this is a big O, here will also become the big O. If we have a construction of lower bound,
I see.
it will count. And a conjecture of Erdős and Zimnowitz states that for any bipartite graph, it has a rational exponent, but it is still open, and it is false for the R uniform hypergraph, but not false for our problem because all the concrete example have the alpha no more than I minus 2. So we make another conjecture to state that if alpha is between this number, the graph will have rational exponent.
Can I have a question?
Yeah.
So you assume that extremal number of family is 1n to the 1 plus alpha, and alpha is less than r minus 1, and does this imply that your family F always contain at least one r partite, correct?
You mean always contains
Yes.
a graph?
R partite, correct?
Yeah, always contains a bipartite graph. If it is no more than this number, this will have the Turán number 0. A Turán density 0. And so the first question is when this lower bound is equal to this upper bound is equal to this lower bound. Actually, this is always true for graph. For r equals to 2, the induced number will equal to the partition number. Because for the bipartite graph, you have only one way to partition it. You can check it, it's not hard. But for I, at least 3. For some graph it is true, but for some graph it is not true. We give a example for they are not equal to each other. We see this graph. And we take all of the age exactly every row and column exactly once. First, so each edge exactly contains exactly one vertex from this set and this set, these four sets. Each time they contains exactly one vertex. So the partition number will equal to 4. The only partition will be this 3 part. But the independent covering number will be the 3 vertex in the first line. So one is 3, one is 4. They are not equal to each other. So our first open question is, for the graph they are not equal, which one is the true bound for P is large? And another problem is that I just mentioned here. Exponent conjecture. I will not write down it. We ask for every family with the lower bound at least the n to the I minus 2, whether it have with a rational exponent. And our second result is for the case P equal to 1 over I minus 1 minus alpha. We give some example to
Sorry.
support this conjecture.
So the rational exponent conjecture is due to Erdős-Zsimonowicz, or is this your conjecture? You just say that the graph results that.
They state it for.
Oh,
I
they
equals to
stated
2.
for graphs, and you know
Yeah,
you're.
we operate it for hypergraph
I see.
with this condition. Alpha is between
Yeah,
I minus 2.
but there's a counterexample if it's less than.
Yeah,
that.
for
I see.
yeah.
So you're generalizing.
Yeah.
So the conjecture is that every rational number in that interval.
No, every
you-
graph
you-
have a rational exponent.
Every graph has a rational
Yeah,
exponent,
another-
not the other way around.
Yeah,
Okay.
If alpha is in that range, then it has to be rational.
yeah.
Mm.
And our second result is for this case, P equal to 1 over I minus 1 minus 2, alpha. So we prove it for some special family. The first one is the family of cycles, given cycles. And the second result is for 6 cycle.
So that's L over L minus 1?
And
The subscript is L over L minus 1.
Yeah. Initially I thought like H minus 1.
Yeah, it's a little hard.
L over L minus 1.
N over
No,
N.
no.
Your
L.
P. P and the 1.
P
Theorem 2, 1.
0 to 1.
P is L over L
Yeah,
minus 1.
P is this number. P equal to L over L minus 1. And in this case, it is equal to n to the 3 over 2. So this case is all for the p equal to this number. But actually we don't know the lower bound for the family of the even cycle. So we need to assume the family of the even cycles has the Turán exponents, this number. Then you will get this number.
So
So
there
for cycle, we only know the upper bound for alpha, is this one. We don't know the lower bound.
So this theorem two, this is actually contingent on some other conjecture. It's not unconditional result. Like this first line up here.
So this is bigger one.
Okay.
This is
That is the.
sorry. And the last one is for S bounded with the graph has one side maximum degree S. So every vertex in this side has at most S degree. This means S bound. Bounded, S bounded. If the graph is S bounded, then it is no more than, here the P will equal to the S, and this will be this number. And for some spatial graph, this will be tight. For some complete bipartite graph, when one side is very large. But the problem is for almost all of the bipartite graph, we don't have the lower bound. So we can always give the upper bound for this problem. In the remaining time, I will give the proof of these two results. The reason we can prove this result because we have a very strong lemma from the Freddie, Noro, and the vertex. They state that every 6 cycle free graph, you can delete half of the edge to make it become C4 free. And they can also make sure each vertex degree will lose at least half. So if we have a graph which is C6 free and has this p-normal number, then we delete the sum of the edge to make it C4 free. Because each vertex keep half of the vertex degree, so we only lost a constant factor. Then we use the faster result to show it is no more than this number. So this strong theory give us proof of the theorem 2.
So you said the lower bound was already known.
The lower bound is just from actually we have lower bound for this.
For C4 you have.
This one we also have because the star will give the lower bound.
I see.
we don't have the Turán graph, but we have the star. The star will give the lower bound of this graph.
You mean star means that one side is just.
Yeah, one side is. But we don't know whether this is better.
I
Yeah.
see. We don't know what.
We don't know whether this number can be smaller.
Ah.
If it is smaller, this will become to this one better. This one will be better. If alpha is smaller.
So what is star, by the way?
Just
Star
only
start
one.
this graph, this construction. This construction will always give us a lower bound. This one.
But this is both graphs, right? So this.
Yeah.
One vertex.
Just minus one.
It's n minus one.
N
So
Every 6 for graph. Using this theorem and theorem 2.1, we get the theorem 2.2. But for longer cycle, it is open question. I think it is even harder than our computer.
Is it a really difficult theorem, or is it?
This one.
Yeah.
This is proved by some structure exercise. It's remember they proved that if the graph is C6 free, then it must consist of many structure. Then they can delete some part to make this, and C4 free happened. But for the longer cycle, it not work. Yeah, now we prove the 2.1. For conveniently, let's see. This is the family of the cycle of length no more than 2L. I need to use a new. First, we assume G is bipartite C equals to every, and it has P into the P. here P is equal to L over L minus 1. The reason we can assume it is bipartite is you can randomly take a bipartite subgraph. Then here you will lose a factor. It's same as the graph contains half of H. You can contain half of this number of the P normal. So we can assume this graph is bipartite. And then we want to get some contradiction. Then we define this is the number of the work. The work means the V1, V2, VL plus 1, and each VI plus 1 is the H. But some vertex can be the same vertex. If it is a path, means the vertex should be different. And also we have the path PL plus 1. To prove our result, we only need to show that the number of paths is larger than n square. If this is larger than n square, you can find two paths share the same endpoint. And because this graph is bipartite, so it will contain a shorter cycle here. If you can find two paths, maybe some of them will be same vertexes, but it will give you a shorter cycle. So we only need to show this result. And to prove that, we first show this number is large. The number of work is large.
So you want to prove the number of paths is
Larger than n
and square, so that there is a pair of vertices.
The two paths share the same endpoint.
Same endpoint, I see.
Then it will give you a shorter cycle here.
Mm-hmm.
Where is the shorter cycle?
This cycle is of length 2L, but maybe some vertex is same vertex. Maybe look like this, look like this,
So
but it contains some cycle.
Yes, since you have a closed work of length
So
2L, so there should
2L
be
is
a,
that's
2L.
the
2L.
number, I see.
So
it's,
shorter cycle.
It's getting
And
confused with the L plus 1
bipartite.
to 2L plus 2 to L.
Yeah.
So it's
So
2L.
this means none of L.
Yeah,
This is the number of
I'm
vertex.
happy. Yeah, I understand that.
okay.
Yeah.
Okay.
No.
Then we will prove this. First for
I'm always confused.
L equals to 3. For L equals to 3, the number of three work is equal to this number. So you first take the H in the middle, then you take this vertex and this vertex. So you have this equality. And this is at least 2 square UV du negative 1 by Cauchy-Schwarz inequality. We just move it here and use it. We have this one. And for this, how many times this one counts for the UV? So for fixed V, we count it dV times. So this will equal to V dV times dV. And this one will equal to U du negative times du. This is clear. This one will be equal to n. And this one will equal to the 3 normal. Have a power of 2. And this one we have the lower bound. Here p is 3/2, so this will be 1 squared. So p equals to, here p equals to 3/2. This will become into the 2.
Wait, it's 3. So it's norm of the G with the 3 high, right? And it's
So is there,
yeah, so you wrote 3 there, but isn't it 1.5?
Oh, so
Oh yeah.
sorry. So here is 3/2. Here 3/2. This is the definition of the P normal.
What was the last? Can you explain the last equation? So you said it's n least n squared. Why? Where is it?
Because the P normal, we assume it is n to the P.
Oh, so that's it.
P is equal to 3/2 for the 6th cycle.
Oh.
so we assume L
Oh,
is
we are
equal to
assuming.
3.
I see.
Yeah, we assume
Okay.
L equals to 3. And for larger L, we will use classical results of validation knowledge. And several years ago, suppose K is at least here equals to 1 integer. And K is even or L is odd. Then the number of well, at least have this inequality. And this case is proved by the erudition and this knowledge. And we conjectured it for this one. And reserved by in several years ago. Yeah. And use this result. We have L plus 10 over N. Actually, we used this case. L is odd. This maybe here L is K here. The L here is a K here. And the here L will equal to 3. We'll take it to 3. 4, 2, N 1 over 3. We have this. And this, we have proved that it is at least this one. G 3 over 2. We need to move some n to this part. Then we have this. This part. Use this result. We have this. And use the convexity we have. This is at least P over N. This is decrease when P decrease. For larger L, P will be smaller.
Confused here. So okay.
This is convex.
Is it
And this will larger than unto Great. That's great.
Do you want 1 over P or?
Oh yeah, 1 over P. 1 over P.
P, 1 over P.
well
What is that? Our assumption is that
P
P
P
is
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 L.
over L minus 1.
L over L minus 1.
Wait, then the L is large, then this is smaller than 3 over. Is it this convexity? When P increase, that number decrease, isn't it?
When P increase, this number will increase. It increase with P.
That means.
Yes, sorry.
Is that the correct direction?
It's just A, P.
Oh, I see. So
Over 1
3
larger
over 2
than
is bigger than P, so therefore it's okay. Yeah.
Yeah, for Q decrease, if Q is lower than P, this inequality.
I see.
Oh, maybe the average.
Yeah, something like that.
Yeah. So we have this. And the next step, we will we want to show the maximum degree is not very, can be not very large. No more than this number. With a small epsilon. If we have this, then we can prove the number of the work is not path will be small. If we have this, maybe we don't have time to prove it.
Okay. Is there a typo with claiming the walks of length L plus 1 should be at least what? So when L is 3, it should be at least n squared.
This number, this will imply this one. Nice. If here it is n squared, this will be n to the L minus 1 over L. Here is n to the p, then it will be n over n to the 1 over p will be n to the, because p is L over L minus 1. So this will give us our claim. Not it is at least, sorry.
Right.
Actually, n is 1
P minus, yeah, okay, I see. So because the P norm is n to the P, so divided by n is n to the P minus 1, and then over to the 1 over P power is n to the P minus 1 over P.
So that means
It's
W
over
L
1
plus
over P,
1.
Yeah, if W is n to the n square, here will be n to the 1 over
Yeah.
L. Here will be this one. This is n to the p. N to the p times 1 over p will be n. This will be n to the 1 over p. 1 over p will equal to L over L minus 1. Will equal. Two sides will equal. So will give us this. And now we assume this. We have no time to prove this part. The maximum degree cannot be very large. Actually, I will give a sketch of this part. We have a U and we have a V. If this part, we are divided into 3 parts. This is degree larger than n to the 1 minus epsilon. This is n to the 1 plus 1 over L plus epsilon. We will prove that these 2 parts will contribute not too much of our function, so we can delete it, and also for this part. Then we get a graph has a bounded maximum degree and also have the p-normal of the lower bound. If we have the maximum degree, then
So you might have to modify your graph. You might have to modify your graph to get this space.
yeah, you
Just
then
cut
we-
off those parts.
we have a subgraph G prime satisfy maximum degree condition and
And
that condition. Then use this result. Then the p will plus 1 will larger than minus the work have some 2 vertex are same. So this is at most this is a way to choose the 2 vertex, and this is a way to take every vertex 1 by 1. The first vertex we have n choice, and another we will have this one. Because we assume the Vi is equal to Vj, so this will only have L minus 1. and this will equal to n times n L minus n plus epsilon. So if epsilon is very small, this will very small than smaller than n squared. Then n squared minus larger than n squared. Here we need some constant. C constant. Yeah.
So can you explain what you mean by L1 plus 1 choose 2? So you are choosing two vertices on the path?
This
On the
part
work?
means the work have two vertex sim. Two vertex sim with two vertex is sim.
Oh.
So this
I
is
see.
how many way to choose these two
I see.
vertex.
Okay.
And if we fix it, when we have chose this vertex will only have one choice. So here we save some choice for the path. Then we can prove the number of paths will larger than n squared. Yeah. So this finishes the proof. And for the cycle, the problem is for all of this result, we have also for some proof here, it is also work, but finally, even we get two paths, we cannot find a cycle with exactly none of 2n. We can find two paths. So we're also interested in the case for cycle, for longer cycle, but we have no way to. Yeah, that's all.
Thank you. Any questions?
So this, I mean, big zeta is because of the this step or the last step, I mean, about the inequality about the P and W, or the some additional condition about the modifying the our graph to make the maximum degree small.
What's your
Mm.
question?
Sorry. So what is, I mean, so up to the upper part, we still guarantee that the ends, the constant is just one is would be enough, but in the where we lose the constant factor of the n squared, not the n squared, about the bound. I mean, when we consider about the upper bound, where is the exact part we lose our constant?
You want to know the constant?
Yeah.
Actually, here will give us a constant. Here we lose a constant, given constant factor,
Okay.
but not factor part. Here is also a given n to the p part, and here also. So three parts will together give us n to the p, the constant of the n to the p.
Also the first part, right? When you assume the graph is bipartite, you're
Yeah, also
Okay.
the first.
That's true.
Yeah.
So if we consider what the P norm Turán density, we can define, right? So then is it continuous function with respect to P?
Continue. So sorry, what is your question?
So if we define a P norm Turán density,
P normal Turán density.
yes, then is it continuous with respect to P?
You mean our result, whether continue?
Yeah, continuity. Okay. I mean, at least we know that the right continuous or the left continuous because of this convexity, right?
Or we don't know. If it continue here, we'll not have a jump. If this is equal to the exponent, will be continuing.
But we want to fix our f first in
So you want to fix
F
the
is fixed,
graph?
right?
Yeah, F is big.
F
Okay,
is
that's
fixed.
also F is fixed, right?
Yes.
You're talking about the non-degenerate regime?
Okay, sorry. So yeah, okay, yeah, that's right, okay. That already
Right, any other questions?